we have identified two conditions to characterize valid steps along a descent direction. The two Wolff conditions. The first condition forbids steps that are too long. And the second condition forbids steps that are too short. Now, when we will put the two conditions together, the key question is, are these two conditions compatible? Meaning that are they steps that verify both of them? And the answer is yes, and we will see in which circumstances this will happen. So the first Wolff condition requires a sufficient decrease in the objective function, and the amount of decrease that is requested is proportional to the slope of the function, proportional to the step, and to a parameter which is strictly between 0 and 1. The second Wolff condition imposes a sufficient progress of the iteration, and in particular, a relative increase of the directional derivative of at least beta 2, and beta 2 again being between 0 and 1. So now we need to check the compatibility of the Wolff conditions. The theorem that guarantees this compatibility is referred to in the book as Theorem 11.9, and it says that if the function is bounded from below along the direction, and if the two parameters are such that beta 1 is strictly less than beta 2, then there exists at least one alpha that verifies both conditions, and an alpha which is positive. That's what we will try to show in this video. The first thing to note is that the first Wolff condition is guaranteed to be verified for some steps. If we have this configuration where we have alpha at the x-axis and f of xk plus alpha dk the y-axis, because it's a descent direction, the Wolff condition will be verified by all the steps smaller or equal to eta. So actually, Taylor's theorem guarantees us that such a eta exists. And actually, I refer you to either the Theorem 211 in the book or the video which is presented in the week Objective Function and which is entitled Gradient and Descent in order to see more details about these results. Okay, so this is a known result. Good, so we have the guarantee that at least the first Wolff condition is verified for a set of steps. Okay, so this is the first Wolff condition, so on a nicer picture. And now we will use the first assumption that the function f is bounded from below. Because this line here is going down all the way to infinity, if the function f is bounded from below, at some point the line will cross the function. So in this case it happens here. Okay, so we have the guarantee that such a point exists because the function is bounded from below in the direction dk. So we call this value of alpha here alpha 1. Now we will use a result called the mean value theorem. Because the function is differentiable in this interval, it means that there is somewhere between 0 and alpha 1 a value of alpha, which we will call alpha 2, such that the slope of the tangent of the function is the same as the slope of this line. This is called the mean value theorem. So here, this should be somewhere, I don't know, somewhere here, let's say. Okay, so this is the tangent, and we choose the point where the tangent is exactly the same slope as the line that defines the Wolff condition. So here we call this point alpha 2. So the mean value theorem tells us that the slope of this line is the same as the slope of this one. So the slope of the Wolff 1 line is equal to beta 1 times the gradient of fk transpose dk. And this is equal to the slope of this line, but the slope of this one is the directional derivative. So it's equal to the directional derivative at alpha 2. So we can calculate beta 1 from this, right? Beta 1, the directional derivative at alpha 2, divided by the directional derivative at alpha equals 0. But this is exactly the ratio that is involved in the second Wolff condition. So it means that if beta 2 is strictly greater than beta 1, then automatically the second Wolff condition will be verified. So we have seen that if the function is bounded from below along the direction dk, and if the parameters of the two Wolff conditions are chosen such that beta 1 is strictly less than beta 2, there exist steps that are verifying both conditions. And in practice, this will give us the idea to take beta 1 close to 0 and beta 2 close to 1, so that many steps will actually verify the two conditions, and therefore it will be easier to find one using a trial and error algorithm, as we will see next.